How does FEM handle nonlinear material behavior? Imagine trying to predict how a metal will bend or stretch when pushed too hard. That's where the Finite Element Method, or FEM, comes into play. It's a powerful tool used in design and analysis to understand stress and deformation in structures. But when materials behave in a nonlinear way, things get a bit more complicated. So, how does FEM manage these tricky situations? Let's break it down. First, FEM divides a structure into small pieces called finite elements. Each element has nodes where calculations happen. When dealing with nonlinear materials, the key is that the properties of these materials change as they deform. Unlike simple elastic materials that stretch proportionally to the applied force, nonlinear materials can yield, creep, or show superelasticity. This means the relationship between stress and strain isn't straightforward anymore. To handle this, FEM uses special models called constitutive models. These models describe how materials respond beyond elastic limits. For example, plasticity models simulate how metals permanently deform after yielding. Viscoelastic models account for time-dependent behaviors like creep. These models are more complex and often depend on the current stress or strain state, not just initial properties. The process involves applying loads gradually in small steps. At each step, FEM updates the material properties based on the current stress and strain. It recalculates the stiffness matrix, which is like the structure's resistance to deformation, to reflect the new material behavior. This way, the analysis captures how the structure responds as materials yield or deform plastically. Because the behavior is nonlinear, simple calculations won't do. Instead, FEM uses iterative solution methods like the Newton-Raphson technique. This method repeatedly adjusts the solution until the equilibrium equations are satisfied within a certain tolerance. It's like taking small steps to find the right answer without overshooting. Another important aspect is that many nonlinear materials depend on the loading history. For example, if a metal is stretched and then released, it might not return to its original shape. FEM keeps track of this history to accurately predict phenomena like hysteresis or permanent deformation. In practical terms, this approach allows engineers to simulate real-world scenarios. For instance, when designing a metal component that will experience high stress, FEM can predict when and where it might yield. It can also simulate how polymers creep over time under sustained loads or how rubber materials behave in biomedical devices. When analyzing a stent expanding inside an artery, FEM accounts for plastic deformation of the metal, large displacements, and contact forces. It updates the model step by step to ensure all nonlinear effects are captured. This makes the simulation more realistic and reliable. Overall, FEM handles nonlinear material behavior by breaking the problem into small, manageable steps. It uses advanced models to describe complex responses, updates the system equations continuously, and employs iterative algorithms to find accurate solutions. This process is essential for designing safe, efficient, and durable structures where materials often go beyond simple elastic limits.